Dear students, we come to the last part of our discussion on chapter 1 essentially, which I wrote as lecture 1, RN the prototype space. So we are going to talk about what is called a bounded set. You know what is a bounded sequence? Bounded set is quite a similar definition. So you can always find a number k greater than or equal to 0, such that whenever x is in S, norm x must be less than equal to k. So you may ask why I am not taking k strictly greater than 0. Suppose actually by k I essentially want to mean a kind of supremum of norm x, right? Supremum of the set of all absolute values, the norm values. So in that way, suppose S consists of the number 0, the origin, 0 vector. Then if I take k equal to 0, the inequality would be satisfied. So those are for the special cases I have put k equal to 0. In most cases k is positive. Okay. So a set which is closed and bounded is called a compact set. A compact set, this is what is a compact set in, the no definition of a compact set in uh, finite dimension, but when you go to infinite dimension, things rapidly change. The notion of a compact set and notion of a closed and bounded set are two different things. Every compact set would become closed and bounded, but every closed and bounded set would not be compact. So sometimes I also, when I look at two issues in infinite dimension, I feel it's kind of a fantasy land. But of course, fantasy land which is guided by logic. So one of the central results in analysis, as Corner wants to say, is this result which says that if I have a set C in Rn, I have to write it closed and bounded set C in Rn, and f from Rn to R is a Rn to Rm. So Rn to Rm is a continuous function, and possibly I should write capital F. Then the image FC is closed and bounded. I think the better thing would be to write capital F here, but okay, I've just written it, doesn't matter. So you know it's Rn to Rm. So for the image of a set FC, which means that it's collection of all those y's, such that y equal to fx for x element of C. So take every x element of C and see what is that fx. So collect all such fx's in one set, and that is what is called the image of C under the mapping F. We have to prove FC is closed. So proving a closed set is simply this, that we have to take a sequence in that set which converges to some vector, and we have to prove that that vector is lying in that set. So you see in the proof that yn is a sequence with yn of course in FC, the image, and yn goes to y star. What we want to show is that y star is in FC. So now yn equal to xn and xn is in C, and C is bounded. So xn is also bounded sequence, and there is a convergent subsequence xnk of xn which converges to some x star, and because C is also closed, x star is in C by the definition of closed set. Now y of nk is equal to x of nk. Of course, for every yn there is a x actually, which we write as xn because we want to maintain an index for which yn equal to that f of x. So whatever corresponds to n, that x is called xn basically. So what we have done, so yn is equal to fxn, xn is a bounded sequence, as a bounded sequence, and hence has a convergence sequence by Weierstrass theorem. It converges to convergence subsequence by Weierstrass theorem, and that subsequence is xnk, which converges to x star, and so we can write ynk equal to fxn star. But you know, ynk being a subsequence of yn, and since yn goes to y star, I know that ynk also goes to y star because yn actually converges to y star. So what I get by the continuity of f, limit as k tends to infinity, f of x and k is equal to f of x star. So y star equal to f of x star if I run the limit as k tends to infinity on both sides. So we have just spoken about the notion of continuity and its sequential definition, that whenever for any sequence xn converging to x star, f of xn converges to f of x star. So y star equal to fx star, by the definition of the image set, it is clear that x star is element of C. If x star is element of C, then f of x star is, since x star is element of C, it is clear from the definition of Fc that y star is in Fc, and that is what we had to prove, and hence Fc is closed. So now we have to talk about the reverse one, right? Now first we started with closed and bounded set, and then we are going to prove that we have proved that the image is closed. Now we are going to prove that the image is bounded. So f is C is a closed and bounded set in Rn. F from Rn to Rm is a continuous mapping function, and the image Fc is closed and bounded. Closed has been proved. I hope you have understood it. So now we are going to talk about boundedness. So we need to show that Fc is bounded. Let us assume that it is unbounded. So when you are speaking of unboundedness, I can obviously find a sequence yn in Fc such that norm of yn goes to infinity. So yn is equal to fxn, xn is in C, C is again closed and bounded, is bounded. Then again I have to take a subsequence, and the subsequence goes to some x star and all those things. But I will not do that re-leveling every time. We just, for the moment, without any loss of mistake here, without any loss of generality. So sorry, without any loss of generality means without any mistake, we can always write for the moment, for this particular setting, that we will take xn to be convergent. Actually I am taking a subsequence, but I am not re-leveling. So xn converges to x star, and also x star converges. So xn converges to x star because C is closed, x star is going to be in C. Now you can write it in terms of subsequence yourself, so which I am not going to do. Now noting that f is continuous, what I will have? Norm of yn equal to norm of xn. So limit of norm yn is equal to limit of norm xn, because norm is a continuous function, which I have given as an exercise to prove. I guess norm is a continuous function. Should be able to prove that. Now I can switch limit of f and xn. So limit of f of xn, because f is continuous, is fx star. So first here we interchange the norm and limit, then we interchange f and the limit. So you get fx star. But what is limit n tends to infinity yn? It is infinity. So there is a contradiction here. So hence this is bounded. The Fc is bounded, right? We started with a contradiction, and we started with the opposite thing, that the Fc is not bounded, and came to a contradiction. This is called proof by contradiction, which is one of the greatest tools the mathematician has. Now we come to a very important results, which takes us to the starting point of a amazing subject called optimization, which is a central tool, or the central mathematical toolkit for an economist, and an economist should actually know this theorem. For example, the Weierstrass theorem is something so important, which we have also learned. It's one-dimensional version when you study calculus, which is so important that any economist should be able to remember this result, even if he is blindfolded under a shower with a gun on his head. So, means you might think that that's a very bad analogy to put somebody under the shower with a gun on his head, but it's a kind of way of telling you that you cannot forget this theorem. That would be not done for an economist. So, what it says that if you have a continuous function from Rn to Rn, and C is a closed bounded subset of Rn, so then f is bounded over C. Basically, if you want to minimize or maximize the function f over C, then the value of f is bounded over C. That there is a capital M, say, for which f of x is less than equal to M for all x in C, and f of x is greater than equal to, say, small m, which is the lower bound for all x in C. So it will have a bound. But what is important is that the bounds are attained. Means there is an x1 in C for which fx1 is less than fx, and x2 in C such that fx2 is bigger than fx. So x1 gives me the lower bound, f of x1 gives me the lower bound. So x1 is actually the minimizer of the function f over the set C, and x2 in this case is a maximizer. We are essentially talking on maximizer on the whole space C. So we will speak about all these things in slight detail about global, local, all these things, global minimizer, local minimizers in the next study about derivatives, optimization, convexity. But here, let's try to do the proof. So, what does it mean? So, if you have a continuous mapping and C is a closed bounded set, just in the theorem just presented before this, what we had learned that the set FC is bounded. So, f of C is a bounded set of real numbers, right? So, which means every bounded set of real numbers has a supremum and an infimum. Those who remember what they have learned in calculus, math 101, which means what I said, there is a supremum, there is a capital M such that f of x is less than or equal to m, and there is a small m such that small m is less than or equal to fx for all x. So that is the meaning of, so this boundedness of the image set Fc tells me that f of x for all x in C has bounds, right? Basically what does it mean? Mod of fx would be less than some m, capital M. So fx would be less than capital M greater than or equal to minus m. So upper and lower bounds are there always. So essentially Fc has a supremum and infimum, and so the bounds are there. So it is bounded on C. Now you have to prove that okay, there is a point which maximizes, which attains that particular bound, and which gives me the supremum value, the functional value at that point at C. So x1 is in C, at which the function value is the minimum, at x2 is another point where the function value is the maximum. So there are one point where the minimum value is achieved, the small m, and another where the functional f of x1 is small m, there's x2 where f of x2 is capital M. So we will not talk about the maximum, I'll just speak about the minimum. So what happens? You take alpha to be the infimum of C. If you remember the definition of infimum. Infimum means the greatest lower bound. Anything greater than that cannot be the lower bound. So let me take a decreasing sequence epsilon k strictly bigger than 0 and epsilon k going down to 0. Now by the definition of infimum, whenever I increase the value of alpha by say a small amount, alpha plus epsilon k, that alpha plus epsilon k cannot be a lower bound. So there must be an element xk in C for corresponding to that epsilon k, such that f of xk is strictly less than alpha plus epsilon k, but strictly greater than or equal to alpha. Alpha is the infimum in any way. It has to be strictly bigger than or equal to alpha. So which means whenever there is an element xk in C such that f of xk is strictly less than alpha plus epsilon k, which means alpha plus epsilon k is not the infimum. The meaning of the greatest infimum or greatest lower bound means if I, however small margin I increase the value of alpha, that value cannot give me a lower bound. There must be some element whose value would be strictly less than that. So what we have created a sequence of fxk which converges to alpha. Because I am decreasing the value of epsilon k, I am decreasing the value of epsilon k. So I am essentially getting a sequence, right? So what I am getting as what I've created is a sequence f of xk. So where is f of, because epsilon k is decreasing. So if we take the limit of f of xk as k tends to infinity, this side it goes to 0. So alpha less than equal to limit of fxk less than equal to alpha, because epsilon k goes to 0. So the limit of fxk is alpha. You can do it in whatever way you please, it doesn't matter. So so what we have done is we have created a sequence fxk such that fxk goes to alpha as k tends to infinity. Now since C is closed and bounded, the sequence xk is bounded, and there is a subsequence by the Bolzano-Weierstrass theorem which converges to x1, right? So fxkj, because it is the subsequence of f of xk that converges to alpha. So as j tends to infinity, right, since f of xkj also converges to alpha, and as xkj converges to x1, by continuity of f, we have f of x1 equal to alpha, because limit of f of xkj is equal to alpha. Because f is continuous, I can interchange f and the limit. So it will become, because xkj is going to x1, so f of xkj, the limit k tends to infinity f of xk, j tends to infinity f of xkj is nothing but f of x1. So f of x1 is equal to alpha, because limit of f xkj as j tends to infinity is alpha. So what does it mean? Alpha is anyway infimum value, so fx1 is less than equal to fx for all x element of C. Your job is to handle the maximum one, the same kind of argument. So here I'll have two problems to discuss, which you can try. So suppose that a company sells a product. I had made up this problem on basis of a problem which was given in the book by Rangarajan Sundaram, which is a beautiful book on optimization, especially for economists, and in fact even for math students. Suppose a company sells a product, and the profit of the company is a continuous function of the product manufactured. So you'll profit, the more you manufacture, possibly the more you can sell and more you can make money. So the amount that you can manufacture, your profit depends. Suppose you are a fantastic hot selling item and every day your things are sold off. Now if your production decreases, your amount you can sell is less, and hence your profit will decrease, right? So the profit is obviously depending on the choice of how much you have produced. So the profit function Vx, where x is the quantity of product manufactured, will for some reason assume that V0, V0 is strictly bigger than 0. So kind of there's an initial endowment basically. Initially have some money. Then assume that there, which can be used for production or whatever, and all these materials. Assume that there is x star such that V of x star is greater than equal to 0, and V of x is strictly less than 0 for all x strictly greater than x star. So if I get out of x star, once I have produced x star amount of quantity, producing anything more would actually make the product worthless, because my profit would become negative. So if my profit would become negative, I cannot run an enterprise. So the question here is, does there exist an amount of the product? Is there a amount I should manufacture so that my profit is maximized, so I can keep on manufacture that amount? So if I decrease or increase the product, my profit would decrease. That's the idea. And if I keep on increasing my product and make it more than X star, then I lose my profit. So does there exist such a amount that the company should produce to maximize its profit? The second problem is more mathematical. This is an economics problem, but you will see how easily you can argue its application of the Weierstrass theorem that you have just learned. So now you consider a function. So here the function v is from R to R, because you are just considering one product that is manufactured. So not many. So let us consider a function f from R to R, where fx is e to the power minus x and c is between 0 and 1. Now show that f is bounded over C. Even though C is not a compact set, the function f is bounded over C. So even though f is not a compact set, this is bounded over C, and you have to discuss this in the light of the Weierstrass theorem. The function is continuous, the set C is not bounded, but is the bounds attained? That's the question. C is bounded because I think I have put 0, 1, right. So is the bound attained? That you have to figure out. You can take 0 to infinity also, no problem. Then also the question would be, is it bounded? If it is the bound attained? Yes or not? And why you think they are not attained? What is the issue? That is the thing that you really have to discuss. The set C is actually bounded. Okay. So with this we end this chapter 1, and we next move over to derivatives in the next class, which the lectures will be put up again on Sunday. Thank you very much. Thank you for your attention.